Well, hello class, this is lesson 2.2a and we're trying something a little new today. I learned how to put video in my screencasts so that you can see my face. Now, I don't like looking at it because see I have this little double chin here. It's really kind of annoying me. So we're going to see how long I can do this. I feel really silly. I'm in my study, just in case you wanted to know. So the walls are kind of bland right now. So let's see how this does, and please give me feedback. I did not know that the clicking of the pen was bothering you guys, so we're trying this on my iPad with a new handy dandy stylus. See, yay! So maybe it won't click as much. So let's see how it goes. Okay, so one important class of density curves is the normal curve. Let's see if this thing will write. The normal curve. Sorry, this one is not quite as precise as the other, so I'll keep trying. I'll keep trying to work on that. But the normal curve represents a normal distribution. Now notice I've capitalized the word normal. It is actually a technical name, normal. Yes, I know it doesn't make any sense, but you're going to find out we have a couple of strange distributions in statistics. One is the normal distribution with a capital N because that's its name, and another one is actually called the students, S-T-U-D-E-N-T-S, students distribution, but also is a capital S because it is a technical name. Now, here are some normal curves that I have put in for us to look at. There's a normal curve here, and we have our other one here. And these normal curves, which we saw on our video with Elise Passetti or whatever, Prelise, what's her name? I can't remember. You know, on the video we watched in class, these normal curves differ only in their width, their measurement of spread. So in these two normal curves, we see some important facts about normal curves. First of all, they are symmetric. Same shape. Whoops. And overall, we would call them bell-shaped. And the normal curve is completely described by giving its mean and standard deviation. That's almost like its name and its middle name, mean and standard deviation. The mean is located at the center of the symmetric curve and is the same as the median. The standard deviation or sigma controls the spread of the curve. Let me erase that. That's not very pretty, is it? All right, and so we abbreviate this normal distribution. This is like its name right here. This is how we would say its name. It would be normal, N for normal distribution, mu, comma, sigma. So it's N for normal, and then you put your mean and your standard deviation. Now remember, this is like its name, its first and last name. I mean, no, let's say first and middle name with a last name of N. Now, why are normal distributions so important in statistics? Well, they really are, and they're going to be key in a lot of things that we do. So you want to get used to looking at them and seeing instances where we find normal distributions. Also, they're just easy to work with. If you have a normal distribution, you've got a center of 0 with standard deviations. It's easy to do all sorts of calculations, which we're going to see in this section. All right. The other thing is that they're really good descriptors. I don't know why I put descriptions, but they're good descriptors for distributions of real data. SAT tests and IQ tests actually have a normal distribution, which is interesting, especially with SAT tests, because we wouldn't think that they would be. But if you go overall a country, SAT tests are very normal and very bell-shaped, meaning there are few very high scores and few very low scores, and most of the people are right in the middle. They are also good for repeated measurements of the same quantity, such as biologicals, whether you're measuring the heart rate in water flea, or if you're measuring height in a middle schooler or a high schooler. All of those biologicals, they're good repeated measurements. When we take them over and over again, we tend to get a normal distribution. They're also good approximation of chance outcomes, i.e. probability, gambling kind of situations. And also many statistical inferences are based on normal distribution. So even if something's not quite normal, if it's close enough, we can do a lot with it. Now the normal curve is also called the Gaussian curve. Or the, I don't know, normal curve, also called the Gaussian curve. I'm not quite, or the Gaussian distribution. Wow, can't even remember what I wrote. And this was used to describe the small errors made by astronomers and surveyors in repeated careful measurements of the same quantity. Now this is from a man named Gauss, and he lived 1777 to 1855. And we see Gauss in a lot of things. This is actually your technical, very long equation for finding area under the normal curve. Now, good for you. You will never actually do that. But I did want you to see how detailed and how incredibly long it is. Notice that we have a natural log in it, some fun roots with pi. It's a big old equation. Thankfully, we have calculators to take care of most of that for us now. Now, all normal curves have certain things in common, and Gauss came up with this specific rule, which is very important in our study of normal curves, and it's called the 68, 95, 99.7 rule. Yes, this will be on your exam. And all this is Gauss noticed that when he was looking at these standard curves, 68% of the data fell within one positive and negative 1 standard deviation from the mean. He also noticed then that 95% of the data from here, from 2 standard deviations to 2 standard deviations to negative 2 standard deviations, covers 95% of the data. And then 99.7, almost all of the data is contained within 3 standard deviations. Now that doesn't mean that there is not data out in the wings, even above 4. We just usually don't see it. And in fact, in some cases, we only look at data going, say, 3.49 standard deviations from the mean. But Gauss came up with this concept of the 68, 95, 99.7 rule, which allows us to estimate the amount of data within a distribution. So, 68... It is so hard to write with this thing, guys. 68% of the observations fall within 1 standard deviation of the mean, mu. 95% of the observations fall within 2 standard deviations of mu. And approximately 99.7 fall within 3 standard deviations of mu. So, from here, -3 to here, that contains 99.7% of all of the data that we gained. Now, this is not always used, you cannot always use this. Remember, this is only for what? Normal distributions. All right, so here's an example of how we use this. The ITBS scores, which is a standardized test score for 7th grade students in Gary, Indiana, is close to normal. Suppose that the distribution is exactly normal with a mean of 6.84 and a standard deviation of 1.55. We'll want to sketch a normal density curve for the distribution of test scores. Label the points that are 1, 2, and 3 standard deviations from the mean. Well, first of all, I want you to notice down here, I have already drawn this. Actually, I didn't, but I cut and pasted it, so it's close enough. And you'll notice that I have a normal distribution curve. When you sketch these, they may not come out like this. That's okay. It's your own sketch. Now, I want you to notice right in the middle, I have put the mean, which is 6.84. And then what I have done is I have added the standard deviation of 1.55, and I have added it here to 6.84. I added 1.55 and I get 8.35. Then I add it again, I get 9.94, and again 11.49. And then going the opposite direction, I subtracted it. Now what that gives me is that this is 1 standard deviation, 2 standard deviations, and 3 standard deviations. -1 standard deviation, -2 standard deviations, -3. Get the hang of it? All right, so what percent of the ITBS scores are less than 3.74? Well, if you'll notice, here's 3.74, which is really, really tiny, a tiny amount. And we know that that's falling on the -2 standard deviation line. So I know that since the whole middle section, the middle 2 sections from here, from this, and it's really hard for me not to show you this, from, oh, wow, there's all sorts of new ones. What does that do? Oh, lightsaber! Oh, wow. Okay, I'm having way too much fun. You know, can I just tell you that the version of this on the iPad is way better than the Android? Okay, so I will change off that because that is just weird and probably making you feel awkward. Okay, we'll go back to our pointer, our laser pointer. Now notice in between a plus or minus 2 standard deviations, we said before was 99.5%, or 95%, which means that the leftovers here, here, and here would be how much? 5%. That's right, boys and girls. So from here, this part right here, and this part would be 5%, so half of that would be how much? Yes, 2.5%. So 2.5% of the scores are less than 3.74. Now we can do the same thing again, trying to determine the percent of scores between 5.29. Oh my, I should really move this picture up, shouldn't I? Well, that helps a little bit. Between 5.29, which is right here, and 9.94, which is right here. Now, we know that the middle section here, this middle section here is 68% of the scores. It's about. And then we know that from the 2 standard deviations, then we have 95% of the scores. So the difference, if we did 95 minus 68, we get some number that I have not written down, nor do I have a calculator. Let me see if I can figure this out. Hold up. And we're back. I don't think my video is going to come through, but so you can see my face and my finger. 95 minus 68 is 13.5%. So what we're going to do is we're going to take the 68% and we're going to add just this part, which is 13.5%, and we will get a grand total of, I don't know, 81.5, does that sound right? 81.5%. So that's how we can use this approximation in order to figure out area. All right, So 98, 68, 95, 99.7 rule is only for our friends, the normal distributions. But there's another guy, he's actually one of my favorites in statistics because I like to say his name. It is a great name, and you will like to say it as well. Pafnuty Chebyshev. Pafnuty Chebyshev is actually Russian. He's one of our founding fathers of statistical data analysis. And there's a picture of him up in our classroom, so you can look at him. Or you can just walk around and say Pafnuty Chebyshev because it makes you feel smart. I think actually last year's statistics class, that was the only guy that remembered all year. All right, Chebyshev came up with a similar rule, which applies to all distributions, even if they are skewed or unimodal, bimodal, whatever. And basically what he says is the proportions of observations falling within K, that is the number, K being the number of distributions, of standard deviation, of the mean, is at least 1 minus 1 over K squared. So, in other words, if we wanted to know what is the percentage of, let's say, K being 2 standard deviations, we'd say it's 1 minus 1 over 2 squared, which is 1 minus 1 over 4. So 70.75 or 75% of the data would fall within 2 standard deviations. And I know what you're thinking. You're thinking, no, Miss Byrie, you just told us that 95 was within 2 standard deviations. And you're absolutely right. But don't forget that this is for all distributions, not just normal. So it's important for us to understand this is a good approximation that we can use. Now, Chebyshev is not on the AP exam, but he is an important person that you should know. I'm not going to ask you a whole lot about this, but I may or may not, I will probably have one test question on this. So it's nice because we can be very specific. I could say that K was 2.35. And so I would just do 2.35 and I would square it. And I get 5.52. So I take 1 divided by 5.52. Okay. Minus 1. So this would be that 82% of the data would fall between 2.35 and negative 2.35. So it's kind of a handy little thing. But remember, as George Box says, all models are wrong. Some are useful. Okay, so let's do check your understanding. This is actually found on page 114, in case you wanted to know, in your book. The distribution of heights of young women aged 18 to 24 is approximately normal with a, what does this number represent? Mean of 64.5 and a standard deviation of 2.5. So make sure that you can understand this. Definitely on the test. Okay, so let's sketch a normal density curve for the distribution of heights. Now, my curves are never pretty, especially when I'm writing with this weird funky pen. Funky pen, woo-woo. But it matches my iPad, just in case you wanted to know. So here's my axis. I know that my center here is going to be at 64.5. And then I'm going to find my other points by adding 2.5. And I get, I don't know, I get 67. 67. And if I add 2.5, I get 69.5. And if I add 2.5 again, I get 72. And then likewise, if I subtract, I get 62. And then I get, what, 59.5? And then one more down here, I get 57. So here's the top of my curve going down. Top of my curve going down again. I know it's not pretty. All right, but I have basically sketched it. Now remember, I always want to annotate. So down here, and I'm going to have to write this here because I ran out of space. This is the height in inches. I would put that right over there. and moving my, you know, I've got these questions down here that are in the wrong spot. All right, so this is height. Here's my normal curve. You can see my mean and median, which should be in the middle and should be the same. So what percent of young women have heights greater than 67 inches? All right, well, 67 inches, right, is within 1 standard deviation of the mean. So within 1 standard deviation. So we know that within 1 standard deviation of the mean, we have 68% of the data. But we also don't want to use both sides of that. We're really only looking at this amount. So what we're going to do is we're going to say, okay, it's 1 minus 0.68 because we don't want this middle section. We're really looking at this section here and the outer sections here. So we're going to subtract what we know, which is 68, from 1. And then we're going to divide it in half because we only want this half, this upper half. So if you do that, you get 0.16, or 16% of the young women have heights greater than 67 inches. Now let's look at, I'm going to try to get us a better color here. Let's look at the percent of young women who have heights between 62, okay, this is 1 standard deviation, and 72. Wow. 1, 2, 3. So I'm going to use all 3 of these standard deviations plus 1 of the bottom ones. So a tricky little problem here. Well, first of all, we know that 99.7% of the data lies within the plus or minus 3 standard deviations, right? So I want half of that because I really am interested in getting all this in here. So that's half of 99.7, which is, I don't know, some weird number. Let's look on my little calculator. It's really tiny. You want to see it? Woo! 99.7 divided by 2 equals 49.85. So that's 0.4985 for this half. But then remember, I'm going to use half of a plus or minus 1 standard deviation. Now, plus or minus 1 standard deviation is 68%, so I'm going to use half of that. So I'm going to add this to 68% divided by 2, which is 34.34. So I add those two together, and I get 80, no, what do I got? Yep. Somehow, yeah, that's right. I have 80.84, about 84% of young women have heights between 62 and 72. Now, the ability to see bits and pieces of this standard deviation curve is going to become really handy next lesson when we get into normal calculations. Oh, I guess that's the end of the slide. I keep trying to add one more. So this is very odd, and I don't know if this recorded the first time, but if it did, that's great. If not, we'll find out. I hope you enjoyed this video, and I hope it helps to have my face, even though I feel awkward in it. Have a great night. See you in class.